All right, day 28. Today we're talking about a technique that's absolutely fundamental for evaluating any machine learning model, cross-validation.
Okay, picture this. You've just trained a new model. You run it on your test set, and boom, 95% accuracy. It feels great, right? But here's the nagging question. Is your model actually that good? Or did you just get lucky with the way you split your data?
Well, that's exactly what we're going to tackle. In the next few minutes, you'll understand a simple method that helps separate skill from luck. You'll walk away knowing how to get a performance number you can actually trust.
So let's start with the core problem here, which I like to call the single score problem.
You see, a single test score is really just one data point, and like any single data point, it can have high variance. Maybe, just by pure chance, your test set got all the easy examples. Your model looks like a genius. Or maybe it got all the weird, tricky edge cases, and your model looks worse than it really is. What we actually want is a reliable estimate, something stable and trustworthy, an average that gives us a much less biased measure of our model's true skill.
And that really gets to the heart of it. We're not just testing one specific model that we trained. We're trying to assess the entire design, the algorithm, the architecture, the features we chose. And to be confident about that design, you have to test it more than once. Okay, so if a single test is unreliable, how do we build a more reliable one? The core idea is surprisingly simple. It's this. Instead of one big, high-stakes test, what if we gave the model several smaller, different tests? And then we just average the scores. That's it. This simple act of averaging helps to smooth out the randomness of any one particular split.
I love this analogy because it makes so much sense. A single trained test split? That's like a final exam. A student could get lucky, right? The exam just happens to cover the few topics they studied really well. But what's a better measure of their knowledge? A series of quizzes throughout the semester. That tests them on everything. Cross-validation? Well, that's like giving our model that series of quizzes.
All right, we've got the intuition. Now let's put a name to it and look at the formal procedure. This is called K-fold cross-validation. So K-fold cross-validation is just a standard way of doing what we just described. It's a resampling procedure. The K is just a variable. It stands for the number of groups or folds that we split our data into. So if you hear someone say 5-fold cross-validation, they just mean K equals 5. Simple as that. And the whole process just means we're going to train and test our model K different times. Okay, here are the steps. It's a really systematic process. Step 1, you shuffle your dataset randomly. You don't want any pre-existing order messing things up. Step 2, you split that data into K equal size chunks or folds. Step 3 is the loop. For each fold, you're going to treat it as the test set, and all the other K-1 folds become your training set. Step 4, you train a brand new model on that training set, you test it on your holdout fold, and you save the score. And this is super important, then you throw that model away. Its job is done. Finally, step 5, you just average the scores you collected from all K runs. That average is your final, much more reliable performance estimate.
You know what? This becomes crystal clear with a quick example. Let's imagine a tiny data set, just 6 data points, and we'll set our K to 3.
So we've shuffled our data, and now we split it into 3 folds. As you can see, fold 1 gets 2 of the data points, fold 2 gets the next 2, and fold 3 gets the last 2. Notice that every single data point has a home in exactly one fold. And now for the main event, the rotation. In our first run, we'll train our model on folds 1 and 2, and we'll test it on fold 3. We record that score, let's call it score 1. Next, for iteration 2, we train on folds 2 and 3, and this time, fold 1 is our test set. That gives us score 2. And you can probably guess the last one. We train on folds 1 and 3 and test on fold 2. Every single fold gets its turn to be the test set, just once.
So, what's our final answer? It's not score 1, or score 2, or score 3. Our final robust estimate of how well our model design performs is just the average of all 3 of those scores. Okay, so that's the how. Now let's talk about the why. Why is this so common in practice?
Well, there are a few huge reasons practitioners rely on this. First, as we've said, it gives you a much more honest estimate of how your model will do on data it's never seen before. Second, it's absolutely essential for comparing different models. If you want to know if Model A is truly better than Model B, you compare their cross-validation scores, not a single test score. And third, it's a critical part of hyperparameter tuning, finding the best settings for your model. So a natural question is, what number should I pick for K? Well, it can depend on your data size. The go-to number you'll see almost everywhere is 10. Using k equals 10 is a very common and very reliable starting point.
And there's a good reason for that. A lot of research has shown that using a k of around 5 or 10 just seems to hit a sweet spot. It gives you an estimate that isn't too biased, but also doesn't have a crazy amount of variance. It's just a really solid, battle-tested default.
All right, let's wrap this up with a one-sentence summary. Cross-validation gives you a robust estimate of a model's performance by training and testing it on multiple, different subsets of your data.
And the key takeaway, the one thing to burn into your memory is this: don't trust a single score. An average performance calculated across multiple tests is always going to be more reliable.